and a plagioclase-rich wall rock that could also precipitate this mineral spinel. Now, the significance of these data is the fact that the pixel size from orbit is about 250 by 250 meters. And we're getting definitive signatures of spinel, orthopyroxene, and olivine over these areas. What we don't know is the geologic context of these. Have they been intruded into the crust? Are they a layered intrusion? We don't know. We need to do good old-fashioned geologic field work on the lunar surface at some of these sites to truly understand their origin and how they evolved. This would also include sampling. You could have very strategic sampling by an astronaut that would allow us, as we saw with 15415, that would allow us to get a much better insight into these new lithologies that we knew nothing about until the Chandrayaan-1 mission. Japan also had a mission, Kaguya, affectionately termed Selene, and what we see from the data that they produced is that they focused a lot on the crust. And we see that there is a dichotomy between the composition of the crust on the near side with that on the far side. We knew that there was a thickness dichotomy, as we see with the Mulmari on the near side and less on the far side. But what we can now see through compositional evidence is that the Selene mission has showed us that the far side crust is more magnesium than the near side. And it may be the magnesian anorthosite rather than the Pharoan anorthosite is the dominant composition on that thicker crust on the far side. Now, this has implications of when plagioclase comes out of our magma ocean. We would have to have a much higher aluminium content in that magma ocean to affect that. But magnesium anorthosite means that it comes out much earlier in the sequence than does the Pharoan anorthosite that we've modeled using the Apollo data. So if we look then at the feldspathic highlands, we can see here are the Apollo data, but we've now got these lunar meteorites which contain an awful lot of highlands materials. They are representative of the crust in the area from which they were derived, but we just don't know which area they were derived from. We can assume far side, but where on the far side, we don't know. So if we then take these two fields, you can see here the Apollo magnesium suite and the Pharoan anorthosites, and we compare those with the data that have come from the feldspathic or highlands lunar meteorites, you can see that these are predominantly Pharoan anorthositic. However, they greatly expand that range of Pharoan anorthosites that we got from the snapshot from the Apollo samples. The problem here is that the Apollo samples have been affected by the Imbrium ejecta. They form a very narrow field that we now know is narrow because we can compare them with these feldspathic meteorites. So the lunar meteorites then are showing us that Apollo gave us a snapshot that was, again, not representative of what the rest of the moon actually is. So the models that have been developed during Apollo now have to be adjusted on the basis of new data. If we then look at what we did learn from Apollo, we can see that the differentiation mirrors that from the big intrusions that we have here on this planet. The ones that we have from the still water are not from a magma ocean. They are a large intrusion of magma. And you can see similarities in the trends there of the rock minerals in the rock types that come from still water with those from the Apollo samples. If we then compare that with the lunar meteorites, we see that the lunar meteorites show a much more a broader field in terms of magnesium number in our mafic mineral for a very narrow range of anorthite content in our plagioclase, expanding it. So we have to adjust our story now because Apollo didn't tell us everything. The new data are now testing the hypotheses that have been developed, such as the lunar magma ocean, by these new samples and the new orbital data. So in summary, The Apollo and lunar missions to the moon greatly increased our understanding of the moon. We knew nothing really about the moon until we had these samples coming back. However, since then, we've now recognized that we have new samples in lunar meteorites. We've also had a lot of missions, a lot of international interest in our moon now, and a lot of international missions have gone to the moon, and the orbital data shows us that the models previously developed are somewhat lacking. They're being tested, and they need adjusting, or they need to be rethought altogether. We also know that while the meteorites are from the moon, we don't know where on the moon they're from. They're from unknown locations. We need to actually have coordinated sample return from areas well away from Imbrium and the ejector from that Imbrium basin. And especially, we need to go to the far side and see whether or not we can actually correlate the compositions from these lunar meteorites with those that are collected in situ from the far side of the moon. Now, the geologic context of these new samples is critical for developing these new predictive models. We want predictive models because on Earth we have plate tectonics, and we know what plate tectonic setting to go to get resources. If we're going to use the moon to go further out into the solar system, we need to develop infrastructure, and that means living off the land and defining resources. So understanding these new lithologies, how they fit in to the given framework of lunar petrogenesis, is going to be important, and it's going to require geologic field work. And probably the best way to do that is by sending astronauts there who are adequately trained to undertake such an expedition. Now, the geologic context of these new samples is going to be critical for understanding and making predictive models. On Earth, geologists have done field work for many years and have developed these models based around plate tectonics. So if we can recognize a particular setting on Earth, we know where to go and look for specific resources that will fuel our economy. Same as can be said for the moon. The resources will become important as we expand into the solar system. And geologic fieldwork is going to be critical to that. It's going to be required to develop these predictive models. If we can then find out where these resources are, things such as aluminium, titanium, water ice, so on and so forth, we then can start to develop an economy behind that. Because it's not NASA's job to go out and mine regolith. This can be brought in as a commercial venture. We can start to expand the space economy. We can start to then bring in private industry, which is going to be employing people and going to be starting to hiring new people to do that, and thus creating jobs that are going to be a necessity as we become a spacefaring species. As we expand to the moon to go on to Mars, the resources on the moon can be used to enable Mars. For example, if we look at building structures on the moon for infrastructure, 3D printing becomes important, and knowing that there's titanium and there's aluminium and there's silicon and there's water ice on the moon becomes important. Being able to harness these resources requires commercial participation. So NASA can then expand onto Mars, but can then buy the services and the materials required in order for example, water is a good radiation protection. We can sheath a spacecraft in water. Launching it from the moon, it's much cheaper than launching it from Earth. We know that the water ice is there now. We can then expand upon that. So by building a spacefaring species, we then enable a new sector of our economy. We expand that space economy. And with the USA being in the forefront of this, this is something that we can lead the world to do. And I think it's important that we use the moon as a stepping stone to do that, although I hate the term stepping stone. It becomes an enabler to do that. The moon is an enabling asset in order to not only go on to Mars, but to expand our space economy into something that is robust and growing, so that graduates from my university, when I ask them, what do you want to do after Notre Dame? They can say, I'm going to go work on the moon. And that becomes science fact, not science fiction.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1,000,000 miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Six, 5, 4.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts.